Good morning, everybody, and let's continue today to talk for Cieliebak.
Yeah, good morning. I'm glad you made it. So today I want to talk about the restricted free body problem.
I hope one day someone will come and will tell us the three-body solution.
Yeah,
Who knows?
that would be nice. Yes. So for that you'd have to just.
But then we lose our jobs.
Yeah, exactly. So then, yes. So I was just going to start with showing you. So we've seen repeatedly the pictures of the two-body problem of the solutions. So those I can easily draw on the blackboard. They're in plane and they're moving on an ellipse, and that's it. And here's just to show you a typical solution of the three-body problem. So you start with some initial condition somewhere, and then you let it go, and you can watch simulations online, and it may even start out moving nicely on an elliptical orbit or around one of the two heavy bodies, and then at some moment it slightly deviates, and then all hell breaks loose. Yeah. So it's really fun to watch some online simulations of it. Yeah. So it looks a bit more complicated, and I think I will switch to the blackboard with that. Up. So the first observation about the three-body problem is that, at least on first glance, it does not look to be integrable. So what if we count integrals of motion? In a three-body problem, then we have the energy, which is one integral of motion. We have the linear momentum, which is 3. We can again use it to switch to center of mass coordinates and just look at the relative motion, so we got rid of that one. And then we have angular momentum still left. And as we've seen, this is vector valued, so it's 3 quantities, but they don't Poisson commute. So in essence, it's really only 2 independent integrals of motion, maybe the z component and the absolute value of the angular momentum. And then nobody has found any other integrals. Yeah. So for the two-body problem, those were enough integrals. So the number of degrees of freedom, on the other hand, in the three-body problem is 3 bodies times 3 coordinates for each of them. Yeah. So this is the number of degrees of freedom, and so we see that this is not enough. Yeah. So unless somebody at some point finds some other integral like the Runge-Lenz vector, but that is not independent of the other ones. Yeah. So some other independent integrals, it seems not to be integrable. And in fact, one can prove, and the first to prove that was Poincaré, is that in general, the restricted three-body problem has no analytic, meaning real analytic, integrals of motion beyond these. Okay. So that is a theorem which can be proved. Nobody has been able to prove that there cannot be smooth C-infinity integrals of motion, because that's just unclear how you would do that. But this is Poincare proved early on, and I will say something about that, but in not Poincare's original proof, but I will mention some approach to this, which is slightly different. So what is the restricted three-body problem? I have not yet said what the word restricted means. Three-body problem is clear. So what is the restricted three-body problem? Well, we have three heavenly bodies which are moving, and the assumption is that the mass of one of them is much smaller than the other two. So you look at the limiting case where the mass of the third body is much smaller than the first two. And then you can consider this body as, this system as follows, that the positions of the first two, so the motion of the first two particles is not affected by the third one. That is what this assumption means. Yeah? So you can first solve for the two heavy bodies, M1, M2, and their positions. So they move on Kepler ellipses around their center of mass. So let me draw it here. So we have that motion takes place in a plane. So here's the center of mass, and then one of them is moving on an ellipse like this. The other one, let's say the other one is maybe quite a bit heavier, so the other one will move on a smaller ellipse, and at any given time, as we've, well, okay, the drawing is not so, okay, yeah, I think you get the idea. And at any given time, you have one of them here, and the other one here. Yeah? So this is Q1 of t, Q2 of t. This is what the motion looks like. They both move on ellipses, and they always lie on a line through their common center of mass, by definition. So somehow they are coupled, the velocities are coupled such that they always lie on a line through the center of mass. Okay, so that we know. And then there's the third planet somewhere there. And now we can then study the motion of the third planet under the influence of the first two. Now, the first two generate now a time-dependent potential for and forces for the third one.
The third one is in space or in the
is
same
in space.
plane?
It's not in the same plane yet. So we'll come to that. Yes. So restricted just means that we make the third mass much smaller, and then there's a planar restricted, which is when they're all in a plane, and I'll come to that later. So this is still, the third one is arbitrarily in three-dimensional space. All right. So this is governed by the Hamiltonian for the third position. Sorry, Q3 and P3, which is P3 square over 2. So I'll neglect the third mass because it drops out anyway. And then we have minus M1 divided by Q3 minus Q1, but Q1 now depends on time explicitly. Yeah? And then minus M2 divided by Q3 minus Q2 over T. This is Hamiltonian, which is now time dependent, so I should maybe really also put a time dependence here. But the time dependence is periodic, yeah? So it's time periodic. Yeah, so we are in a situation like the one that was studying in Floer homology, in fact, yes, where you also look at time periodic Hamiltonians and treatments if you try to study their motion. So let's look, before I go to the planar system, where all of them are in the plane, I want to go to another special case of this. And this was studied by Sitnikov in 1960, and you find a very nice and detailed discussion of this in the wonderful book by Jürgen Moser, Stable and Random Motions. In celestial mechanics, maybe, or something, yeah? So in on dynamical systems, something like that, you'll find it. This is the following special case. So again, here's a center of mass. Now, one assumption is that M1 is equal to M2, and you can normalize them to 1/2. So they're moving on ellipses of the same type, possibly. Yeah, but so this is Q1 of t and Q2 of t, and you can, and they are both periodic, and you can normalize the period be 2 pi. This is not yet some assumption, but now the assumption is that the third very light body is moving on the line perpendicular to the plane through the center of mass. Okay. All right. So now you see that this is becoming very symmetric, because now the forces acting on this one are, one of them is in this direction and one of them is in this direction, and you get a more symmetric Hamiltonian. So maybe I'm not going to write the Hamiltonian. It's a special case of that one. Okay. So what Sitnikov did is to any motion q of t, he associates a sequence of numbers. So just from the geometry of the problem, we see that this by symmetry, because the forces, when you add the two force vectors, they point along that line. So if the particle starts out on that vertical line, it will stay on that vertical line forever. Yeah? So it will just oscillate up and down on that vertical line. That's the only thing it can do. Right? But because the force is changing periodically, then it will not perform just a regular oscillation back up and down, but it will sometimes be faster, sometimes be slower, and might go further up or further down and so on. Yeah? So the motion is expected to be somewhat irregular, but it will bounce up and down. That's the only thing it can do. Right? And then, so you associate to it a sequence of numbers, sk, k in the positive or negative integers, by saying that, let's denote t minus 2, t minus 1, t0, t1, t2. Those are the times at which, so this, if I put coordinates, then this is the z coordinate, so it's just described by one coordinate, and then this is the times at which z of ti is equal to 0. So those are the times at which it's moving through the plane of the other two bodies. Yes? And so that gives us a sequence of real numbers, and then the S case, we just take the integer parts to get a sequence of integers. So we take, in fact, we take the difference between those. So we take tk plus 1 minus tk. Divide them by, well, this is in the natural numbers. This is positive integers. Yeah, the sequence of positive integers. Well, it might be 0. Yeah, might be 0 or positive integers. Okay, and here's the theorem of Sitnikov. Given a sufficiently small eccentricity, eccentricity means the deviation from the ellipses of being circles. Yes. So I had introduced it before in the two-body problem. So eccentricity is some of the distance between the center of the ellipse and the focal point. Yeah. So eccentricity small but positive. So it's not a round circle. For eccentricity 0 wouldn't work. So it must be non-zero but positive. And there exists some integer m which depends on this eccentricity in natural numbers, such that correct? Yes. Such that every sequence sk with sk greater or equal to this number for all k corresponds to a unique solution Q of t of that system. Yeah. Okay. So you can so these integers, because 2 pi is also the period, so these integers measure like between two successive zeros how many rotations have the two heavenly body performed. Yeah, up to rounding error. Yes. So you can prescribe an arbit. You can say, okay, I'll start, and then at first, the first time it hits 0 should be at time 0, say, and then the next time it hits 0 should be after they have performed 27 rotations, and then the next time it goes through 0 from the other side should be after they have performed 2 other rotations, and then the next time it should happen after they performed 1 million rotations, and so on, right? I find this mind-boggling, yeah? So if you think about it, you prescribe arbitrarily this sequence of numbers, and then there is a solution which is doing exactly that. Okay? And that is chaos, okay? I will not give a formal definition of chaos, but this is a prototypical example of chaotic behavior. Yeah. And well, maybe let me say a little bit more. So one formal way of saying it is that one can say that the system contains symbolic dynamics, or as it's also called, a Bernoulli shift. And Bernoulli shift is an abstract system which, when you first look at it, it doesn't look all that chaotic. But let me say the simplest type of Bernoulli. There's variants of that. Contains the Bernoulli shift. So this is a map. Let me call it sigma, like a shift map on some space, capital sigma. So what is this abstract space, capital sigma? Capital sigma is the space of all sequences Sk, A and Z. Well, you could do it with arbitrary numbers, but the simplest version would just be where you just have numbers 0 and 1, in fact. So let me not call them Sk, maybe let me STU. Okay, so let me call them UK, where the UKs are either 0 and 1. That would be the simplest version. And the shift map of such a sequence would be UK K minus 1 or K plus 1, I think is a matter of convention. So you just shift such a sequence by 1. So sequence consists of some zeros and ones. So there's some ones, then some zeros, some ones, some zeros, ones again, and so on. And let's say this is at k equals 0. Yeah. So we have an origin somewhere here. This is by infinite in both directions, but we know which one is the entry at 0. Yeah. And the shifting is just moving the sequence by 1 factor to the right. I think it's the way I said it. So the next one here would be 0, and then comes 1, 1, 0, and so on. Yeah. Okay. It's very harmless looking, and if you take a sequence of these non-negative integers, you can out of that build a sequence of zeros and ones by saying that you say this is S0, so not very well. S0, S1, S2, and so on. Yeah, and then you shift it, and this is exactly what, if you think about it, what is happening when you follow the system for one period. Then these sequences have been shifted. Yeah. So if you look at it one rotation later, then the sequence of numbers will have been shifted. That the first one has been reduced by 1 and so on. Yeah. So you see precisely this kind of shift. And now this is nice. So you can view this as an abstract dynamical system. So this is a space. In fact, you can endow this space with a metric. You can make it a metric space so that this map becomes continuous. Basically, you just sum over the differences here. You divide by 1 to the 2 over 2 to the k, and then you have a dynamical system which is a continuous map on a metric space, and you can define some properties like sensitive dependence on initial conditions and so on, which capture chaotic behavior. Or you can define a notion called topological entropy, which for this system is positive. That's also one indication of chaos. So you can define various notions of chaos and check them just on this abstract, very, very simple system. So this is some exercise here which you can give to students to work out. Once you give some definitions, they can prove that this has positive topological entropy once you wrote down the definition. And what Sitnikov theorem says, that this system is embedded in this motion of the third body along this vertical line. Yeah? So, for example, because this system has positive topological entropy and so on, then the original system will also have that same property. So this is a property of topological entropy, that if you have a dynamical system, you find a subsystem which has positive entropy, then the bigger one has. It just follows directly from the way it's defined. Yeah? So this is the more precise way, you can, in fact, from Sitnikov's theorem, prove mathematically that this system is chaotic in a precise sense, which I'm not going to define. But
Is there like an estimate on the M zone?
I don't know. No, I don't know. Yes, so when I said you can prescribe it arbitrarily, I said, okay, you say the first one should be 2, or so then I might be lying, yeah? Maybe, maybe they all have to be at least 1 million, yeah? But anyway. Let me add one more thing, that from the fact that you have embedded this Bernoulli shift, this chaotic behavior, you can then also deduce Poincaré's theorem that there are no analytic intervals. Yeah. From the fact that it contains this Bernoulli shift. This is not how Poincaré did it. But Poincaré's idea is very simple. He also found this symbolic dynamics in that system, but he was looking at a different system. I think he was actually looking at a planar system, and he was finding some periodic orbit in the planar system, and then some homoclinic orbit to that periodic orbit. And then near that homoclinic orbit also constructed this symbolic dynamics. So the conclusion was the same, that it contains a Bernoulli shift and therefore cannot have analytic intervals. But it was found in a different special case of this three-body problem. All right. Now, let me go to the system that André already asked about, namely, so it's Cieliebak, it's important to remember these acronyms because people start adding more letters in front of it. Yeah? So the circular, okay, so there's a planar restricted three-body problem, which I probably don't want to explicitly discuss, so let me immediately go to the planar circular restricted three-body problem. So PCR3. Yeah? So this is one of the main difficulties in this area. To read an article where, like in every other sentence, these acronyms appear, yeah, and then different ones and so on. Okay. So what is planar and circular? Well, planar means that the third body is moving in the same plane as the other two. So in the same plane as Q1 of T, Q2 of T. And circular means that the two heavy bodies, they move on ellipses, and circular means that they move on circles. Yes? So if the eccentricity is 0 of their motion. Not necessarily a circle of the same size. So the masses can still be different, but they can still, even if the masses are different, they can, both of them move on circles. Yeah? So this is a special case of, yeah, with two further restrictions. So everything is in a plane, so we're reducing the number of degrees of freedom by just looking at the plane. And it's clear that once the third body starts in the plane, it will remain in that plane. So this is clearly a subsystem. Yeah? And this is an assumption, and we will see why this assumption is very useful to make progress on studying this. And this has no physical justification, in fact, this circularity. The planarity is not so bad, because, yeah, let me maybe say something on that. well, circularity is also not completely far-fetched. Yeah? So, for example, the first body, Q1, could correspond to the Earth. And I will maybe stick with that notation. So I will write it as QE, like the motion of the Earth, and Q2 corresponds to the Moon. I'll write it Qm, like the Moon. And then the third one, Q3, corresponds to some satellite, something that we want to bring from the Earth to the Moon or something. Yeah? So satellite. To have something concrete in mind. And then we can check like how reasonable are these assumptions. Well, the motion of the Moon around the Earth is not so far from being circular. I mean, so it's not totally unreasonable. Another situation would be where the heavy body would be the Sun, the lighter body would be the Jupiter, which is by far the dominating second heavy body in our solar system, and the third one is the Earth or some other body, which in first approximation to study the motion of the Earth you would just study it as going around the Sun, but if you want to do finer calculations, at some point you definitely need to take into account also Jupiter. But again, now the three of them, they do roughly lie in a plane. Yeah, that's not such a bad assumption, and also the motions are roughly circular. Yeah, so it's not very far from reality, but it is an assumption. Okay, so let me maybe introduce some terminology to normalize this a little bit. So let me do a few calculations to derive some explicit form of the body. So let's write QE of t. So this is now in the plane, and I view the plane again as a complex plane, so I can use complex notation. So we write it as e to the minus I omega t times some fixed vector at time 0, and likewise for the Moon. So they go around clockwise. Okay, doesn't matter really. Yeah. And the third body is moving subject to the Coulomb force of those two, which I'm not going to write maybe. And then the center of mass is at the origin. So we have ME QE plus mass of the Moon QM is always equal to 0. So we put the center of mass at the origin. And now, let me draw a picture of just, let's first look at the motion of the two heavy bodies before we go to the third one. So they are somewhere the center of mass is at the origin. So one of them will be maybe closer, the other one will be further away if they don't have the same masses. So they are moving like this and like this. And then they have the mutual attraction, and that must be equal to the centrifugal force. So we can write this equation down. So the centrifugal force is at the Earth is mass of the Earth times radius times angular velocity. That's the centrifugal or centripetal force, depending on how you want to view it. And this must be equal to the gravitational force, which is ME times Nm divided by 2E minus 2m squared. Yeah? Let's denote okay, fine. So this is actually going to be constant. So let's denote this quantity by R. Yeah? And then, what are we going to see? And the same thing is true for the moon, yes? So from this, we see, now if we also write mu, the relative mass of the moon, divided by the total mass, and then 1 minus mu must be the mass of the Earth divided by the total mass. Then we get the equation that the radius QE must be um divided by r square omega square, and the radius qm must always be 1 minus mu times m divided by r square omega square. And if you add up those two masses, you must be getting r. Yeah, not the mass, the two distances from the origin. If you add them up, you get r. Which is, this cancels out, so you get m divided by this one, so you get this relation, omega squared is equal to m over to the cube. And this relation we also all know, this is Kepler's third law.
They are moving with the same angular
Yes,
velocity.
they're moving with the same angular velocity. This is what the same.
Okay.
And they must, because if the center of mass is always at the origin and they both move around, they must move with the same angular velocity. So that, I mean, one is always minus the other one up to scaling.
Okay.
Yeah, because they always lie on a line to the origin. So if one is moving, the other one must move the opposite way, so they move with the same angular velocity. Yeah? Yes. All right. So now let us normalize the initial positions here to put them on the which one? These initial positions to put them on the x-axis. So everything is taking place in the plane. So the absolute value of this one, so this one becomes 1 minus mu times r, and this one becomes mu times r using this relation. Yeah? And so the heavier body, the Earth, is somewhat closer because mu, and think of mu as being smaller than 1/2. Yeah, so this is at, and let's normalize this to put this at minus mu times r. So this is the Earth. And we have the moon somewhere further away at 1 minus mu times r. Yeah? So this is so you see the relative masses also determine the positions of the two with respect to the origin. So this is the okay. And then let me maybe I don't have to. Right. And the third one is now just moving somewhere in this plane. And now, because they both move with the same angular velocity, it's natural to try and switch to rotating coordinates, because then they become stationary. Yeah? They already made a drawing which suggests that we want to view them as being stationary, and this will be true if we rotate the coordinate system along with their motion. Yeah. Now comes the difficult part, which always killed me in my physics lectures. That if the motion is, the motion is clockwise this way, then we should move the coordinate system with that one, and then the coordinates themselves will transform the opposite way. Yeah? So this is an absolute killer, but I do the computation and it'll come out right. Yeah. So let's do the time transformation. So we switch to rotating coordinates. The coordinates of our third body we're calling qs of t, and I introduce new coordinates q of t as e to the I omega t qs of t. Yeah. Okay. And now the only question is, do I have to put a minus there or not? And I claim that if I do this, then it comes out right. Okay. So let's work out the equation of motion. So those would be the coordinates in the fixed coordinate system, which is fixed in space and not rotating. And this would be the coordinates in the rotating coordinate system. Yeah? And they differ from this one by this transformation. Now let's work out the Newton's equation in the rotating coordinate system. So we need to compute first and second derivative of that. So let me just do it for once. Yeah? So q dot is I to e to the I omega t qs dot plus I omega qs, or which I can also write, inserting this back, is e to the I omega t qs dot plus q. Right? That's right. Times I omega. Yeah? Okay. Q double dot. I need to take a derivative of this one. So it's e to the I omega t. And I'll do it from this form here. Let me copy it, so otherwise I will screw it up. So I get q s double dot plus twice I omega qs dot minus omega square qs. Okay. Now what is qs double dot? This satisfies Newton's equation. So qs double dot is equal to the force, time-dependent force acting on qs, where this is the gravitational force generated by the two bodies. And I will write it in a moment.
Plus the centripetal force.
Not this one. This is in the fixed coordinate system. There we just have a gravitational attraction. There we only have, so this is just the gravitational force. I will insert it, and the centrifugal force comes up. Yeah? But here, no, this is just the usual gravitational force. And I'm going to write it in a moment. And the other two forces are the ones that you want to see. So what we see here is we see this force being transformed by the rotation. So we see e to the I omega t. Then this is the force at time t, the gravitational force. So this is the gravitational force. Applied to qs, and I can write qs as e to the minus I omega t q again. Yeah? So this is how the force will transform. And then we have two additional forces, namely the first one is plus 2I omega. So qs dot. So e to the I omega qs dot is just q dot. And then what do we have here? And then I need to subtract I omega q. Do it right? Using this relation. And then I still have the third term. And qs times this one gives just q. Okay? Deal with this one. So this is the same, the first term just remains. Then we have plus 2I omega q dot. And then we have plus omega square, 2 omega square q minus this one. So we get plus omega square q. So this minus sign goes away. Yeah? We get plus sign. And now we see that this is still the gravitational force, but now being transformed. And I will compute this in a second. But then we get two additional forces, this being the Coriolis force, and this one being the centrifugal force, because we have a plus sign, so that force is pushing outward, which is coming from the rotation of the coordinate system. And this is Coriolis force, which is velocity dependent and orthogonal to this one. Yeah, so Andre will love it because this looks like the Lorentz force. Yeah. Okay. And what is the gravitational force look like? So this one, let me write it here. This one is, if I'm not mistaken, this is minus 1 minus mu times the total mass times let me times Q3 is here. So we have this is the mass of the Earth times this one, and we need to take Q3 minus the position of the Earth. Yeah, so it would be Q3 minus the position of the Earth at time t. So not QC, QS as I called it, divided by QS minus QE at time t cube minus the same thing for the moon. Yeah? And now if we, so this is rotating with e to the minus I omega t. Times the position, yes?
The mass of the moon, yeah? Or
This is the mass of Earth, 1 minus mu.
okay. Yes, okay.
Yes?
Yeah.
1 minus mu. So the mass here is heavier here. But
Yeah.
so this is the mass of Earth. Yeah? So this is what's going, this one times the position at time 0, which was minus mu r. Yeah? And if we now replace Qs by e to the minus I omega t cube, then the minus, and then outside we multiply by I omega t, you see that this goes away. Yeah? It doesn't matter in the absolute value, and outside of here it will just go away. So here, this force now becomes time independent. And that was the whole purpose of this one. We are transforming from a Hamiltonian system with time-dependent Hamiltonians by going to rotating coordinates to a Hamiltonian system with time, where the Hamiltonian now is time-independent at the expense of getting two additional forces. So now we are in a Hamiltonian Hamiltonian system with time independent Hamiltonian, and the Hamiltonian is of the form h of qp. Now qp are the coordinates in my rotating system. This is of the form p squared over, well, okay, let me, if I want to write it as a Hamiltonian, then I need to Okay, so to build the Coriolis force into a Hamiltonian, I'll say a little bit about this in a moment. You can do it by introducing a vector potential for this one, and then we have the potential. Now the potential I can write. So the potential must generate. So the Coriolis force will be in here. Will be generated by this A, which I will explain in a moment. Now all the other forces which show up must be generated by the potential. So the potential will be V of Q. We'll have the gravitational potentials with respect to the Earth and the Moon. So it will be minus 1 minus mu times, so this is the mass of the Earth divided by the distance to the Earth, but now in the stationary system. So this is just Q plus mu r absolute value. Then minus mu times m, this is the Moon. And the position of the Moon is now fixed at 1 minus mu r. And we also need to generate this force. Well, this force is a harmonic force, so it's just generated by plus omega square over 2 q norm square. This will generate this force, and I think I'm doing it wrong. I think it's a minus sign, yeah? Because we take minus the gradient of this one to derive this potential. So this is the potential. Where, again, this is the centrifugal potential, which will generate the centrifugal force. And this A is, now for this one I need to, I think A is, so P minus A, I think, is a vector P1 minus omega, or maybe 2 omega Q2 and P1 plus 2 omega Q1. So the or the other way around. This I'm not sure of the signs. Yeah. So that if you compute the Hamiltonian equation, then this shift here, this is the A, the vector potential, which will then generate this Coriolis force. Now here the notation that I'm introducing a vector potential. This already suggests something that I will go more into tomorrow, because I need to stop. Well, I still have a few minutes, I guess, because we started 4 minutes later. Now this kind of, so this generates the Coriolis force. Now this same kind of Hamiltonian you can now interpret physically in many different ways, because this can also now be interpreted in electromagnetic terms. Yeah? So electromagnetic interpretation of this same system would say that this is a vector potential for a magnetic field. Let's say B. Now here the magnetic field B is just given by the Coriolis force, but this looks like the Lorentz force, yeah? Because it's acting velocity dependent but at orthogonal angles to it, and so this is exactly the shape of the Lorentz force that would be generated by a magnetic field which is orthogonal to the plane in which the bodies move. Yeah? Of field strength omega, this would exactly be the Lorentz force. Well, this here, you can then interpret as electric forces. So those would be Coulomb forces if you put charges at the two positions. Yeah? Instead of putting massive bodies and use the gravitational law, you can just put charges of opposite charge to the moving body. Yeah, if you give the moving body negative charge, you put positive charges in those two positions. You have the same losses. So those are Coulomb forces. And this one, not so clear. Yeah, this one is some additional smooth potential, which I don't know any electromagnetic interpretation of this one.
Be like an elastic force or something.
Yes, it's some elastic force, yeah, but this does not look very electromagnetic. Yeah,
I know, but you could put just a spring there.
Yeah, there could be some other force,
Yes.
but maybe rather mechanical force, which is also there in the background.
Yes, because this interpretation is very nice, because here you are dealing with a non-inertial system of reference.
Yes.
But when you go back to this electrodynamic analogous system, then you can go, that's an inertial system. You have two fixed charges and a magnetic field orthogonal to the plane.
Yes.
And you have a test charge
Yes.
moving in an inertial system
Exactly.
and
yes.
connect to a spring.
Yes, exactly.
So this is Newtonian mechanics,
Exactly.
classical electrodynamics.
Classical
and so-
electrical, but in an inertial system.
Yes,
Exactly. Yes. So
yes.
you can
So-
use this.
You get the same
in a rotating
problem,
system,
but
the same problem in an inertial system, but
inertial
with
system, yeah.
with electric and magnetic
Yes.
forces and some other elastic
Yes.
force. Yeah. So and this was the starting point for some work that I did with Urs and Lei Zhao, that we then went to study such systems in slightly more generality. So this, and we gave them the name Stark-Seemann systems. Which are precisely generalizations of these systems. So you can write them down in higher dimension, but you can also do them in the plane. Let me stick to the plane, which are governed by Hamiltonians precisely of this shape. So the Hamiltonian is P minus, in general, this could be some position depend. Well, here also it depends on the position in a linear fashion. Yeah. So this could be some vector potential, and then plus some V of Q. And what would the general shape of V of Q be? V of Q. Now, this would be a two-center Stark-Seemann system because it has two centers of Coulomb attraction. So this would be of the shape that it's minus some mass, 1 minus, or it could be a charge, it doesn't matter. Let me normalize the mass to 1, Q minus, the first one is the Earth, okay. At some fixed position, it doesn't matter. Then minus mu times Q minus the second one, and then we just add an arbitrary, let's call it V1 of Q, which is a smooth potential without singularity. So those have singularities as two positions, QE and QM in the plane, and this is a smooth potential. Yeah, but everything time independent, and you can then interpret it either as some system from celestial mechanics in a rotating coordinate frame, or as an electromagnetic system in an inertial coordinate frame, or anything else. And I'll talk more about those systems tomorrow. In particular, those systems have a lot of known systems as special cases, and that's where the name comes from. For example, there's a system studied by the physicist Stark. I think they were all studied in quantum mechanics, but they have classical analogs. So the Stark system is an electron moving in the electric field of a proton and an external electric field constantly. I think Stark is an
Stark is
electric field, and then the Zeeman system is an electron moving in the field of a proton with a constant external magnetic field.
Yes.
So those would be special cases of this one. So this would be a two-center. You can also restrict to the case when you drop one of those terms. If you look at the motion which is near one of them, so the other one is far out, not where the motion is ever taking place. So you can put the other one into the smooth potential and just study a one-center Stark-Zeeman system. And this is what I will mostly do tomorrow. Yeah. So so this is a class of systems which I think is quite interesting because it contains a lot of physically interesting systems, both from celestial mechanics and from electromagnetism. And we can say a few things about those systems that are discussed tomorrow in this generality.
In this case, because here you have the magnetic potential,
Yes.
or the magnetic field and the force and so on. What would be the analogous electric force in this potential?
In which one? In this one?
Yes.
No, the electric forces are the two Coulomb forces.
Yes, I know, but to go to that Stark.
To Stark,
Stark had the charge.
It has a constant.
Yes.
So it would be in the Stark system you would have an electric potential in the smooth part would be the field strength times the z coordinate. So that would be the potential which generates a constant. If you take its gradient, it gives you a constant magnetic field pointing in the z direction. So this would be part of this smooth potential. Yeah. So it has the singular Coulomb potential coming from the proton.
Yes.
And then there's a smooth potential which generates a constant electric field, external one. That would be the Stark system. And likewise the Zeeman system with a constant magnetic field. Okay, thank you very much.
Okay, thank you. Okay, since we had already some discussion, let's maybe skip further discussion and make a short break of 10 minutes until 10:15.